This is Swathi, working as assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we will discuss problems on number systems, number-based conversions, and complements. So here, the problems on we will be concentrating more on number-based conversion. That means we will be discussing some problems on how to convert a number from one base to the another base, and also we'll discuss some problems on complements. So first of all, so we know we have different types of number systems which have various bases. So now how to convert a number from one base to the other base. So let us take the first problem. Convert the octal numbers into binary, decimal and hexadecimal numbers, and the octal numbers given are 45.5, this is base 8, and 32.2, base 8. So these are the two octal numbers given. Now we need to convert this into binary, decimal as well as hexadecimal. So first of all, how to convert an octal number into binary? Octal to binary. Octal to binary. How to convert an octal number into binary? Replace each octal digit with its 3-bit binary equivalent. With its 3-bit binary equivalent. Okay, so as we all know that octal number system will consist of 8 symbols. Those are ranging from 0 to 7. In order to represent them in binary, we require 3 bits. So in order to convert an octal number into binary, replace each octal digit by its 3-bit binary equivalent. As we all know that the 3-bit binary equivalents of this numbers, that is 0 to 7. Let us write the 3-bit binary equivalents of 0, 1, 2, 3, 4, 5, 6, 7. So 0 is represented in 3-bit representation as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the last one is 111. So these are the octal numbers or else octal digits, whereas this is the binary equivalent for the octal digit, binary equivalent. So now as I told you that, so first I'm taking the first problem. So what is the first problem? That is 45.5, 45.5 base 8. So now I want to convert this into its equivalent binary. So how can I convert this into equivalent binary? That is 45.5. So each digit of octal number should be replaced with its 3-bit binary equivalent. What is the binary equivalent of octal digit 4? That is 100, and octal digit 5 is 101. Point. This point should be kept as it is, and again 5 is represented in binary as 101. This is the binary representation of given octal number. Now coming to the decimal. How to convert a given octal number into decimal? So what we need to do is we need to first multiply each octal digit with its positional weight, and add all the products, What are the weights here? So as it is an octal number, the weights will be powers of 8. So now I'm taking the octal number 45.58. So now what is the bit position here? After the octal point, the position starts from -1. Before the octal point, the position starts from 0, 1, 2 and so on. So now I have to multiply this 4 with its positional weight, which is 8 power 1, because this 4 is in the position 1, plus 5 into 8 power 0 plus 5 into 8 power -1. 8 power -1 is nothing but 1 by 8. So now 4 into 8, that is 32, plus 5 into 1, which is 5, plus 5 divided by 8. 5 divided by 8. So now I can find out the value of this. 32 plus 5 plus 5 divided by 8 can be, if you evaluate this value, you will be getting 0.625. Now finally the value is 37.625. So this is the decimal equivalent of the given octal number, that is 45.8. This is the decimal equivalent. Now similarly consider the hexadecimal number. So now we are going to find out the hexadecimal number. So how to convert a given binary octal number into hexadecimal? So first we have the procedure, that is, first convert the given octal number into binary. So already we have the binary equivalent, that is 100.101.101. This is the binary equivalent. Now group them into 4-bit binary groups started before. So that means we need to group them into 4 bits. So as here we don't have sufficient number of digits here. So we need to add zeros to the MSB position. So this is one 4-bit group. And here also we have only 3 digits, but I need to group into 4-bit groups. So I'm adding to the LSB side after the octal point. So this is one more group. Now replace each 4-bit group with its hexadecimal digit, its equivalent hexadecimal number. So 0010. So what is this one? This represents 2, and 0101, which is 5, and 1010, it is decimal 10, whereas hexadecimal 10 is represented with A. So and hence I can write the hexadecimal equivalent of 45.5 as 25.8. So this is the hexadecimal equivalent for the given octal number. So these are the procedures. So how to convert a binary octal into binary? Replace each digit with its 3-bit binary equivalent so that you can be able to convert octal number into binary. And the second one is decimal. So how to convert it into decimal? Multiply each digit with its positional weight, that is power of 8, and then add all the products so that you will be converting the given octal number into decimal number. And hexadecimal, how to convert an hexadecimal? First convert the given octal number into binary and then group them and make groups of 4 bits and replace each 4-bit group with its hexadecimal equivalent. So this is the procedure. Now let us take the second problem. So what is the second one? It is given, it is 32.82, which is octal number. So now I want to convert this into binary. First I want to convert this into binary. So now not binary, first I want to convert this into binary. Okay, so the binary equivalent of 32.2 can be given by replace each digit with its 3-bit binary equivalent. So 0, 111 is a binary equivalent of octal digit 3, 0, 1, 0, it is a binary equivalent of octal digit 2.010. So this is the binary equivalent of the given octal number. Next thing, decimal. So how to convert this into decimal? So multiply each digit with its positional weight. So I am going to multiply each digit with its positional weight. So 3 into 8 power. What is the position of this one? This is 0, 1, whereas this one is -1. So 3 into 8 power 1 plus 2 into 8 power 0 plus 2 divided by 8, or else 2 into 8 power -1. So now I can write this one as, or else I will write like this, that is 2 into 8 power -1, because its positional weight is -1. So position is -1 and hence I am multiplying this one with 8 power -1. 3 into 8, that is 8 3s are 24, plus 2 into 8, sorry, it is not 8, 2 into 1 plus 2 divided by 8. So 2 divided by 8 is 1 by 4. 1 by 4 is 0.25. So that is 24 plus 2 plus 0.25. So how much I'll get? 26.25. This is the decimal equivalent of the given octal number. Now coming to the Next one, what is that? I want to convert this into hexadecimal. Hexadecimal. So how to convert? So we have the procedure. So what is that? We need to get the binary equivalent of the given number, octal number. So the binary equivalent given here is 011,010.010. Now make groups of 4-bit each. So this is one group. So as we are lagging with two digits here, so I'm adding 2 digits to the MSB side after the decimal point, that is, and here only 3 bits are there, so I'm making group of 4 bits by adding 1 to the LSB position. So this is equivalent to 1 and this is equivalent to 1010, which is 10. In 10, 10 in hexadecimal is represented as A.4. So that is 1A.4 is the hexadecimal equivalent for the given octal number 32.8. So this is how we can convert a given octal number into decimal, binary and hexadecimal. Now let us see one more problem. Convert 10101101.0111 to octal equivalent and hexadecimal. So we have binary value, so which is 10101101.0111. This is a binary number. So I want to convert it into octal. How can we convert it into octal? So octal can be converted, form the groups of 3 bits each. Form the groups of, we have to remember the procedure, then only we can convert all the things. Groups of 3 bits and replace each 3-bit group by its octal number, by its octal digit. Okay, it's equivalent octal digit. This is the octal to binary to octal. Similarly, hexadecimal. How can we convert it into hexadecimal? So, in order to convert a binary number into octal, what we have done, we have formed the groups of 3 bits. So, the same way, we need to form the groups of 4-bit each. Groups of 4-bit and replace each 4-bit group by its equivalent hexadecimal digit. So this is the procedure. So after knowing the hexadecimal digit, with its for equivalent hexadecimal digit, because hexadecimal, what are the symbols we have in hexadecimal? 0 to 9 and A to F. So that means 0 to 9, 10. A to F are 10, 11, 12, 13, 14, 15. 6. Totally 16 symbols we have. So that is why each 4-bit group, that means each hexadecimal digit can be represented in binary with 4-bit equivalent. So now we have a procedure. Now I am taking the problem. What is the problem given here? The problem given here is 10101101.0111. Now I want to convert it into octal. Okay, so for that 10101101.0111, right? This is a binary. Now I am forming the groups here. So before the octal, before the binary point, start grouping from LSB to MSB. So grouping must be done with 3-bit each. Each group consists of 3 bits. So this is one group and this is one more group. And here we are lacking with 1 bit. So I'm adding one extra bit at the MSB position such that the value will not change. Okay. So now here come after the binary point, again this is one 3-bit group, but this one is left free. So now I want to add zeros. Which side I have to add? We have to add the zeros to the LSB side. After the binary point, add zeros to the LSB. Before the binary point, add zeros to the MSB position. Now replace each digit with its octal digit. So 010, which is 2, and this is 5, and this is 5 again. 0, 1, 1 is 3, 1, 0, 0 is 4. So that is the equivalent value is, that is the octal equivalent for the given binary number is 255.34. So this is the octal number. Now similarly, I want to convert it into hexadecimal. 1, 0, 1, 0, 1, 0, 1, 1, 0, 1.011. This is my binary. I want to convert it into hexadecimal. So now for that, 1, 0, 1, 0, 1, 1, 0, 1.011. Right? So now form the groups of 4 bits starting from LSB to MSB before the binary point. So this is a 4-bit group and this is also a 4-bit group. This is a 4-bit group. Now what is this equivalent? 1, 1, 0, 1. This is 12 plus 1, 13. In hexadecimal, 13 can be represented as A is 10, B is 11, C is 12, D is 13. So I have to represent this as D. Whereas 1, 0, 1, 0, whose equivalent, decimal equivalent is 10. 10 in hexadecimal can be represented as A. Now 0, 1, 1, which is 7. So that is AD 0.7. So this is the hexadecimal equivalent for the given binary number. So this is how we can convert a given binary number into octal and hexadecimal. Now coming to the next problem, write the first 10 decimal digits in base 3 and base 16. So as we all know that we can have a number of any base. So not only octal, binary, hexadecimal and decimal, we can also have a number system of any base. So now I want to write the decimal digits, first 10 decimal digits. First 10 decimal digits means what? Decimal digits are 0 to 9. So how many these are? 10. Okay. So I want to write the first 10 decimal digits, that is 0 to 9 in base 3 as well as in base 16. Now how can I write this one? So here now I'm writing the decimal digits. Okay. Okay, whose base is r is equals to 10, and now we are writing in base 3, that means r is equals to 3, nothing but radix. And now we base 16 is nothing but what? Hexadecimal where r is equals to 16. So how many decimal digits he asked us to consider? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the decimal digits. Now I want to write the equivalent hexadecimal as well as base 3 numbers. Okay. So here one thing we need to remember. So any number from decimal to binary can be converted. Any number, that means any decimal number can be converted into any base by simply performing the successive division. So now I want here 0 in base 3. So how can I do this? Just perform the successive division by 3, because the resulting number system's base is 3. So 0 is very smaller, so I cannot divide this one. 0, and that means 0 times, and that this will be 3. So one thing you have to remember, as it is base 3 number system. So what are the number of symbols we may have? Base 3 number system. So r is equals to 3, and here the symbols that are included in the number system will be varying from 0 to r minus 1, that is 0 to 2. Whereas the remaining all the things will be considered as unspecified. So that means the symbols present in the base 3 number system are 0, 1, 2. Okay. So other than these are not related to the decimal symbol. That means a base 3 number system will have only three symbols. Those are 0, 1, 2. So here now how can I write this one? So 0 and the remainder is 3, and the remainder is 3 here. So sorry, remainder is also 0. So that is why I can write 0 as 0. Now I have to write on the reminders like this. Okay, now 3 by 1. So 3 zeros are, and reminder is 1. 3 zeros are 0, and we have a reminder of 1. So this is 1, or else we can also write it as 0, 1. Next up, here this is 0, 1. Next up, here coming to the next thing, 2. 2 in base 3 can be represented as 2. Okay, because these are the valid symbols. Now 3 we have, I have to divide this one by 3. So then this is a decimal digit, and now I am converting it into base 3. So 3 ones are 3, and the answer is 0. So now the answer will be 1, 0. And for this one 4, it is 1, 1. And 5. 5 in base 3. So 5 is a decimal number. I want to convert it into base 3. So I'm I'm dividing this one by 3. So 3 ones are 3, and the remainder is 2. So now I need to write down the reminders in this track. That is 1, 2 with a 2 with a carry 1. Okay, and similarly 6 can be written as 1, 3 in base 3. 7 can be 0, 4, and 8 can be 0, 5. Just a second. So now, just a second, not this one. So 6, how can I write this one? 3 twos are 6, and the answer is 0. So 6 in binary can be, 6 in base 3 can be represented as 2, 0. 6 in base 3 can be represented as 0. Now 7, 3 twos are 6, and the answer is 1, 2, 1. Okay, next 8. So 3 twos are 6, and 8 minus 6 is 2. So that is 2, 2. I can write 2, 2. That is 8, decimal digit 8 in the base 3 number system as 2, 2. And similarly 9. So I am dividing this one by 3. 3 threes are 9, and the answer is 0. So that is 3, 0. So these are the base 3 equivalent. That means we are converting the decimal digit 0 to 9 into base 3, and these are the equivalents here: 0, 1, 2, 1, 0, 1, 1, 1, 2, 3, 0, 3, 1. 2, 0, 2, 1, 2, 2, 3, 0. So this is the answer here. Now coming to the hexadecimal. As you all know that hexadecimal, we have 16 symbols, and that includes 0 to 9 as well as A to F. So 0 to 9. So these are the decimal digits. So there is nothing change in the hexadecimal digits from 0 to 9. So we need to write as it is. So this is the this is the 10 decimal digits in base 3 as well as base 16. I hope it is clear. Now convert the following hexadecimal number to their decimal equivalent. Now how to convert an hexadecimal number into decimal? Hexadecimal to decimal. Hexadecimal to decimal. What is the procedure? Any number system to decimal can be done by simply multiplying each digit with its positional weight, and adding all the products will give you a decimal equivalent of given number. So that is, multiply each digit with its positional weight. So what is a positional weight in case of hexadecimal number system? It is power of 2. It is power of 16. Power of 16, and add all the products, so that you will be able to get the decimal equivalent of the given hexadecimal number. Now I am taking the hexadecimal number given EAF1 to the base 16. So now I want to convert this into binary. So what are the positional weights here? This is 0, 1, 2, 3. So that means E into 16 to the power of 3, because it is base 16, that is hexadecimal number, plus A into 16 to the power of 2, plus F into 16 to the power of 1, plus 1 into 16 to the power of 0. E is nothing but what? E is 14 into 16 to the power of 3, that is 4096. that is 4096. Okay, and then plus A is what? 10 into 16 to the power of 2, that is 256, plus F is 15 into 16 plus 1 into 1. So this is the multiplication. So now if I multiply this one, if I multiply this one, I will be getting that value as 57344. So that is 14 into 4096 is 57344 plus 10 into 256, that is 2560, plus 15 into 16. 15 into 16 is equals to 240, plus 1 into 1 is 1. So now if I add all these, I will be getting, that is 57344, next 2560, next 240, plus 1 into 16 to the power of 0, it is 1. So now 5, 10 plus 4, 14. So now 5, 10, 11. Okay, and this is 11, and this is 10, and this one is 6. So we will be getting it as just a second. So here 4 plus 1, 5, and then this 4 plus 4, 10, 10 plus 1, 10 plus 4, 14, 10 plus 4, 14, and then 10, this is 8 plus 2, 10, 10 plus 1, 11, 10 plus 1, 11, 11, that is 8, 8 plus 8, 9, 10, 6, that is 60145. So this is the answer, which is nothing but the decimal equivalent of EAF1. The decimal equivalent of EAF1. So this is the answer. This is how you can convert a given hexadecimal number into decimal. So now let us take another problem. What is the Gray code equivalent of hexadecimal number 3A7? Find 9's complement of 21. So let us consider it as first Gray code of hexadecimal number 3A7. So how to convert a Gray code? First, in order to convert a Gray code, we need to convert the given hexadecimal number into binary. So that is 3A716. So we can convert this into binary as 0011, and A is 1010, and 7 is 0111. So this is a binary equivalent. So what we need to do to generate the Gray code, first the given code is converted into binary. So this is the binary representation. How we have converted the given hexadecimal number into binary? Replacing each digit of hexadecimal number by its 4-bit binary equivalent. So this is the 4-bit binary equivalent. Now I am going to find out the Gray code. So this, let us consider this is a binary code, okay, which is having 4 bits, B3, B2, B1, B0. Now I want to find out the Gray code for this one, equivalent Gray code. So equivalent Gray code will also have same number of bits. So G3 can be obtained like this, whereas the XOR of these two will give you G2, and the XOR of these two will give you G1, and the XOR of these two will give you G0. So now, and that means in Gray code and as well as binary, the MSB is same. So 3A7 in hexa is equals to 0011, 1010, 0111. This is binary. Now I'm going to convert it into binary. So Gray code MSB is 0. What is the XOR of these two? 0 XOR 0 is 0. Next 0 XOR 1 is 1. And then 1 XOR and 1 XOR 1 is 0. Now 1 XOR 1 is again 0. 1 XOR 0 is 1. And then 0 XOR 1 is 1. Next 1 XOR 0 is 1. And then 0 XOR 0 is 0. 0 XOR 1, 1. Next 1 XOR 1 is 0. 1 XOR 1 is 0. So this is the Gray code for the given hexadecimal number. 00, 1, 0, 0, 111, 01, 00. So this is how we can convert a given hexadecimal number into Gray code. Okay, so this is, and then the next thing, next we have second problem. The second problem we have is that is 9's complement of 9's 9's complement of 25.639. So how can we get the 9's complement? Subtract 9's complement of any decimal number can be obtained by subtracting each digit of a decimal number from 9. So that is 99.999 minus 25.639. So now 0, this is 9 minus 3 is 6, and 9 minus 6 is 3. 9 minus 5, 4, 9 minus 2, 7. So this is the 9's complement. So that is 9's complement of 25.639 is given by, so how much? 74.360. So this is the 9's complement. That is how we can get the 9's complement of a given number. Now the next problem, sixth one. So what is that? We have to perform the subtraction using 1's complement as well as 2's complement. So what is the procedure for 1's complement subtraction? 1's complement. So 1's complement subtraction. So we have to find the complement of, that is 1's complement of negative number, After that, add positive number with the 1's complement of negative number. While adding these two, if any carry results, if carry, add it to LSB of the sum. LSB means least significant bit. If no carry, result is negative, and it is equals to minus of 1's complement. Again we have to take 1's complement of answer. So this is that means if no carry is generated, then the difference is considered to be negative, and the final result can be obtained by placing a negative sign and taking the 1's complement of answer. So now let us take the first problem, and that too using 1's complement. So now what is the problem given? 11010, okay, minus 10000. So these are the two numbers. Now I'm going to get the 1's complement of negative number. 1's complement. So how can I get the 1's complement? Changing the 1's to zeros and zeros to 1's. So 11010. Next up, what is a 1's complement? As we have 1 here, it will be changed to 0. 111. Now the subtraction becomes addition. So now add these two. 1 plus 0, 1 plus 1, 0 with a carry 1 plus 1 again, 0 with a carry 1 plus 1 plus 1, that is 1 with a carry 1, and then 0 with a carry 1. So now we have a carry here. So this carry is added to the LSB, and this carry is called as end around carry. Now add the carry to the least significant bit. Now 1 plus 1, 0 with a carry 1, 1, 0, 1, 0. So this is the answer here. So that means this is how we can get the answer, and the answer is considered to be positive. Now let us do the normal subtraction. 0 minus 0, 0, 1 minus 0, 1, 0 minus 0, 0, 1 minus 0, 1, 1 minus 1, 0. So this answer and this answer are same. So this is 1's complement subtraction. Now coming to the 2's complement subtraction. Whenever you are doing 2's complement subtraction, so what are the rules that are to be followed? So everything is same. So instead of finding the 1's complement, first find out the 2's complement of the negative number, add the positive number with the complement of 2's complement of negative number. If carry, If there is a carry, then discard the carry here in case of 2's complement subtraction. If no carry, then consider the result to be negative, and the answer will be obtained by getting the 2's complement of the answer and putting a negative sign before. Now I am taking the problem here 1 1 0 1 0 and 1 0 1 0 0 0. So this is a negative number. So now I am taking the 2's complement. So the 2's complement can be 1's complement plus 1. 1's complement plus 1. So what is a 1's complement? 0 1 1 1 plus 1. So if I add 0 1 1 1 plus 1, so what I'll get? 1 plus 1, 0 with a carry 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 1. So this is the answer. So, but here, now I want to add again, okay. So this is the 2's complement of the given number. 2's complement of the given. So what we are doing? We are getting the 1's complement plus 1 we are adding. So here, now what I'll get? I'll get the answer as 1 0 0 0. So this is the 2's complement. Now add all this. Okay. Now I'm taking the numbers 1 1 0 1 0. Next, 2's complement of negative number can be obtained by 0 1 1 1 1. So now add these 1 1 plus 1 0 with a carry 1, 0 with a carry 1, 1 with a carry 1, 0 with a carry 1. So we have a carry here. So this carry, in case of 2's complement, discard the carry. Discard the carry, and the final answer is this one. So this is the actually it is something wrong. Sorry, actually I have taken wrong. So the 2's complement of the given number is this one. 2's complement is this one, right? So I have to take this one. 1 0 0 0. Just a second. 2's complement of negative number. 1 0 0 0. So now 0. Now 0 0 plus 1 1 0 1 1 plus 1 0 with a carry 1. So if we have a carry, just discard the carry. Discard the carry, and the final answer is this. See, this one is same. So like that we can do this one also. So whenever you are doing the problem, first you need to check whether the number is having equal number of zeros, or equal number of digits or not. If it is not having equal number of digits, just add zeros to the required number of zeros to the MSB position. So like that you can do this one. So I'll be telling you for 2's complement, or else 2's complement I'll tell you. 1's complement you can do it. So 1 0 0 0 1 0 0 and minus 1 0 1 0 1 0 0. So this is the answer. First of all, I am going to find this one 0. Okay. So first of all, I'm going to check. I'm going to find out the 2's complement of this one. 2's complement. 2's complement of this one is 1's complement plus 1. 1's complement plus 1. What is the 1's complement of this one? 0 1 0 1 0 1 1 plus 1. So 1 plus 1, that is right. And first of all, let us see how many number of digits are there. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So now I am adding here 0. 1 is changed to 0. 1 0 1 0 1 1. So 0 with a carry 1, 0 with a carry 1, 1 1 0 1 0. This is the 2's complement. Now I am adding these. So 1 1 1 0 0 0 1 0 0. Okay, plus 2's complement of negative number 0 1 0 1 1 0 0. So now add all these. So 0 0 0 with a carry 1, 0 with a carry 1, 1 and then 1 1. So this is the answer. So we didn't get any carry. If I am not getting any carry, then the result is considered to be answer. So the final answer is minus of 2's complement of, because we are finding the 2's complement, I am using the 2's complement. So again I need to find out the 2's complement. of 1110000. So this is now the 2's complement of this one. So 1's complement 000111 plus 1. So how much I'll get? 0 with the carry 1, 0 with the carry 1, 0 with the carry 1. Next, this is 1. Okay, 0 with the carry 1, 1, 0, 0. So this is the answer, right? Put a negative sign before. So finally, I'll get 1, 0, 0, 0, 1, 0, 0 minus 1, 0, 1, 0, 1, 0 is equals to minus of 0, 0, 1, 4 zeros. So first of all, if I find these, what is a decimal equivalent of this one? The decimal equivalent is 4, 8, 16, 32. This is the position. 1, 2, 3, 4, 5, 6. So this is 4 plus 2 power 6. 2 power 6 is nothing but 64. 68 minus, what is the answer here? This is 4 plus 16. That is 4 plus 16 is 20. 20 plus 64, that is 84. So how much is the answer? So 84 minus, this is 64 plus 16. 64 plus 16 is 80. 80 plus 4, 84. 84 minus 68. So how much I'll get? 14 minus 8 is 6. And then this one is 7 minus 1 is 16. So what is the position here? 0, 1, 2, 3, 4. That is 16 minus 16. Minus 16 is the answer. So this is how we can verify the answer here. So this is the 1's complement and 2's complement subtraction. You can perform subtraction of any number of any base using complements by just finding the complement of a negative number and just adding it to the positive number, so that you will be getting the answer. Now the question is, convert the hexadecimal number into decimal number. So the first one, F2816, I want to convert it into hexadecimal. So so what we need to do, we need to multiply each digit with its positional weight. F into 16 to the power of 2 plus 2 into 16 to the power of 1 plus 8 into 16 to the power of 0. So F is what? F is 15 into 256 plus 2 into 16, it is 32, plus 8 into 1 is 8. So now the final answer, we will be getting it, the answer for this one. So the answer for this one is 3840 plus 32 plus 8. So finally the answer you will get it as 3880. So this is the decimal equivalent for the given hexadecimal. Similarly, you can do for this also. BC2 16, I want to convert it into decimal. So B is 11 into 16 to the power of 2 plus C is 12 into 16 to the power of 1 plus 2 into 16 to the power of 0. So 11 into 256 plus 12 into 16 plus 2. So how much I'll get? So 11 into 256 is 2816 plus 12 into 16, that is 192 plus 2. So if I add all this, I'll be getting the answer as 3010. So this is the decimal equivalent for the given hexadecimal number. So like that you can do any conversion. And one more problem. So convert a given expression in standard POS. So this is product of sums form. So we have sum terms. We have sum terms, and all the sum terms are added together, which is nothing but product of sums form. So this is and we are going to convert this into canonical form. Canonical form means actually this function is a 3 variable function, because we could see 3 variables A, B, C, but each term is having only 2 variables. That means one of the variable is missing. So I want to convert this into canonical form such that each term will have all the 3 variables either in its true form or in its complemented form. So for that, what I am doing is I am going to consider, so A, So plus b, which variable is missing? C is missing. So just add add a term formed by multiplying the missing variable and its complement, and then here a into a complement we are using because a is missing, and in the last term we have to use b into b complement plus c. So now use the distributive law. So that is x plus yz is equals to x plus y into x plus z. Now expand this one using this distributive law. So now I can write this one as a plus b plus c into a plus b plus c complement. Now similarly a plus b plus c into a complement plus b plus c, and similarly I can write this one as a plus b plus c into a plus b complement plus c, right? So here now avoid the redundant terms. That means repeated terms, if any are there, just eliminate the redundancy. Consider only one. So as a plus b plus c is repeated for 3 times, I'm just considering it because we know that a dot a is equals to a. So using this property, I'm going to consider only a plus b plus c term once because it is a redundant. So a plus b plus c complement, and then a complement plus b plus c, and then a plus b complement plus c. So finally we can also write it as product of. So this indicates that as it is a sum term, it is taken in true form. It indicates it is 0 0 0. It is 0 0 1 1 0 0 1, sorry, 0 1 0. So that is, I can represent this as m0 and this one as m1 and this one as m4 and this one as m2. So I can write this one as pi capital M of 0 1 2 4. So this is the canonical form or else standard form of representing a Boolean expression which is in the POS form. So this is how we can convert a given Boolean expression into POS standard form, SOP and POS. Okay. So I think that's all for this lecture. So in this lecture we have seen how to convert a number from one number system into other number system, and also we have seen how to perform the arithmetic operations using complements, like using one's complement and two's complement. We have performed the subtraction, and we have also seen how to convert a Boolean expression into canonical form. I think it is clear to you all. That's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.